And first, I would like to thank the organizers for giving us opportunity to participate in such a nice conference and attend several interesting lectures. So basically, today my talk is about simultaneous non-vanishing of central L values with large prime label. As from title, it's clear that I'm going to talk about something non-vanishing of central L values, and it is based on a joint work with Professor Manickam and Balesh Kumar. So basically, I tried to put some introduction here, but there are so many work and so much literature on the non-vanishing of central L values, and so much important. I don't think it needs any introduction to this audience especially. And I was confused which one to put and which not to put, so I didn't put anything. So vanishing, non-vanishing of central L values, it doesn't need really any introduction. And so let's concentrate directly to the objective of my talk, and where exactly, in which corner of the non-vanishing of central L values I am going to concentrate. So let me first clear my objective. So objective is that given a normalized new form of large prime label, so obviously I'm going to talk in label aspect, count the number of forms G of the same weight and label as of F such that none of the twisted central L values by the character chi d naught vanishes. So kind of both doesn't vanish with twist with the same character at the central point half. So I want to make more precise my problem, and for that I have to introduce the terms what I have put in my objective. So I'm going to just quickly recall them. Obviously I won't recall new form, cusp forms, etc., since we have been hearing from first day itself. So let me set up the problem, background of the problem. So let's start with any two positive integers k and n, and S2kn be the space of cusp forms of weight 2k for the group gamma 0 n. Inside the space S2kn, there is orthogonal decomposition, and it decomposes in two subspaces. One is the new form subspace and other is old form space. And with new forms, with the forms in new form space, special things happening and very nice things happening. That's why mainly we concentrate on this subspace of S2kn, that is the new part of the whole cusp form space. And obviously the old forms, they are coming from somewhere lower labels from the divisors of n, from that label, and obviously they will be considered when we consider that particular label in the new form category. So I am going to concentrate on this subspace of the space of cusp forms, that is new form space. And I'm going to, and this new form space has the property that they have a base, an orthogonal basis of Hecke eigenforms. Hecke eigenforms means there are certain Hecke operators. So they are eigenforms for all the Hecke operators at the same time, and they are orthogonal as well. I'm going to put extra condition that I will take orthogonal basis of normalized Hecke eigenforms for S2k nu n with the condition that the first Fourier coefficient is 1. So always that can be normalized, at least in integral bit that facility is there, in half integral bit that is not there. And another notation is that let D be the set of all fundamental discriminants, and for any D in D, we define the character chi D dot, which is D by dot, the primitive quadratic character of conductor mod D. with this understanding, let's start with any cus form, not necessarily new form right now, and let D belongs to the fundamental discriminant with the condition that D is co-prime to the label. And then we attach the L function to F by using the Fourier coefficients of F, that is the usual L function AFN n power minus S. But here I'm going to talk about the twisted L functions by the character chi D. So I consider this twisted L function LSF tensor chi D, which is nothing but chi D n. AFN is the Fourier coefficients of F, and n power minus S plus 2k minus 1 by 2. Generally, it is n power minus S. I am putting this extra factor n power minus 2k minus 1 by 2 to normalize it so that I can shift the abscissa of absolute convergence from 2k minus 1 by 2, 2k minus 1 by 2 plus 1 to half. So basically, I want to come in the scenario of standard L function. So I want to put the line half in place of line k. With and then the completed L function, I can complete it. So this is my L function LSF tensor chi D, and I multiply with the gamma factor with some factor coming from the conductor D and N. Since when I twist F with chi D, it becomes cos form of the label ND square, and it is always under root of the label by 2 pi power S. So that's what it has been put. It has been put here, and this completed L function, as usual, has an analytic continuation to the whole complex plane, and they satisfy the functional equation. This SF tensor chi D goes to 1 minus F slash WN tensor chi D. WN is the usual free k involution on the space S2k gamma 0 n. So this is again a cos form, and it has been twisted by the same character chi D, and this W is the root number, so they are given by chi D of n, tau of chi D square by mod D, where tau chi D is the usual Gauss sum associated to the character D, associated to the character chi D. With this notation, let me go to our problem. So for any F in F2K1, what is F2K1? I don't know if I have defined it already. Yes. So here I didn't put emphasis on that, but F2Kn will denote the orthogonal basis of normalized new forms of the new form space. So basically F2K1, when I take n equal to 1, it is simply the basis of S2K1 consisting of all Hecke eigenforms with respect to all the Hecke operators. In n equal to 1, S2K nu n coincided with the S2K1. So there is no old form coming from the lower label, since that is already label is 1. So now let me start with the label 1. So if I take bait 2k, I collect all the bait 2k label 1 Hecke eigenforms, and let's choose one out of that, any F, and define this RKF to be the cardinality of this set. This set is consisting of all those Hecke eigenforms of bait 2k and label 1, such that the central value of the twisted L function F tensor chi D at half and the central value of the twisted L function G tensor chi D at half, they don't vanish simultaneously. So they are non-zero at the same time for some D in D. So this D is same. So whether this here we want to concentrate in counting these number of these forms. So given F, I want to count the number of G such that L half F tensor chi D and L half G tensor chi D non-zero for some D in D. So basically making the same D for both. If I allow D1, D2, then it is already known that yes, it is happening. So in that direction, the first result, which I would like to mention, due to Luo in 2018, so he proves that given F KK eigenform of weight 2K and label 1, the number of such G who have the same non-vanishing at half is greater than K power half minus epsilon. The constant obviously depends on epsilon. So this is weight aspect result for this for the cardinality of this set. Now, obviously, when we go to the label F2Kn, suppose I take the set of all normalized new forms, orthogonal basis of label n, and I want to talk about the same set and cardinality of this such set, then I have two things, weight aspect and label aspect. So today we want to concentrate in the label aspect, and we are not able to handle with any arbitrary label. We have handled with the prime label only. So throughout now the talk, our label of the cusp form will be prime. So in label aspect, let me formulate the problem. So let P be a prime and F is any normalized new form in S2KP, that is part of the basis of normalized orthogonal basis, and define RPF. So now I will fix K and I will define the RPF, which depends on the label P specifically, that though G in the F2KP, the set of orthogonal basis of normalized new forms of S2K nu P, such that the central L value of F tensor chi D and central L value of G tensor chi D is non-zero for some D in D, and obviously this label should not divide D. That's what we saw while formulating the L function. And now the question is that I want to count such G. I want to give lower bound on that. In label aspect, like Luo has given in weight aspect for the label 1 and weight 2K. So in this direction, the first result is due to Balesh, and this result says that if I start with any normalized new form in S2KP with prime label, with the condition that the eigenvalue with respect to the free K involution of F is -1 power K. So this is kind of in some other term, it is in the minus space, and 2K weights are these many. So you take weights among them only. So fix one of them. Then for any epsilon greater than 0, RPF, the number of G which have the same non-vanishing as F at half, is greater than P power half minus epsilon, where the implied constant depends on K and epsilon. This is in weight aspect. The next result, which we have worked out recently, is about removing these conditions, what is there on F. So to start a normalized new form in F2KP, I don't need this condition F slash that it is in minus space or plus space. It can be anywhere, and K can be anything. Then for any epsilon greater than 0, we have the number of G such that L half F tensor chi D naught into L half G tensor chi D naught is non-zero, is greater than P power half minus epsilon. So no improvement on this side, the lower bound side. Only improvement is removing these conditions on F to start with. So any question? No question. Okay. So now I will move to the proof. So in the proof, what I am going to do, I am basically going to explain the proof of Luo in weight aspect, and I will then in next few slides I will explain how the Luo proof need to be modified to get these label aspect results. Whether in some cases it's possible to modify the same method, and maybe in this last one, our result, it was not possible. So our approach was different. So let me first explain the Luo's idea of the proof, which says that given any f in of label 1 AK eigenform and number of g such that the same such that both the central L value of both the function doesn't vanish, is greater than k power half minus epsilon. So first thing, let's start with any f in f2 k1 label 1 AK eigenform. Now let d naught in D, the fundamental discriminant, such that this condition is there, be the first fundamental discriminant such that L half f tensor chi d naught is non-zero. I want to get for f I want to choose the least d naught in terms of modulus, such that first of all L half f tensor chi d naught is non-zero. So I want to first choose that least d naught. For that, what we do, we know that by using the Walsh-Purge formula due to explicit form of Walsh-Purge formula due to Conan and Jagier, by using that we relate this central value to the coefficients of the half integral weight modular form. So if f is any in f2k1, then under Shimura-Conan isomorphism, we know that there is a half integral weight form in the plus space of label 4, such that the mod d naught coefficient of that half integral weight form square by the norm of G under the Peterson inner product is related to the central L value of f, this twisted L function of f, by the norm of ff. With this, if this is non-zero, this means this has to be non-zero. And when CG of mod d naught is non-zero, the advantage is now I am talking about the non-zero-ness of the Fourier coefficients. And I know that, and since I am choosing d naught least, in some sense, I am trying to get the least d naught, the first d naught. So here CG mod d naught, this is the, I can assume that this is d naught is fundamental, and this is kind of first non-zero Fourier coefficient of G. Since any other, if it is written like this n squared times mod d naught, then this coefficient has relation with the coefficient of f with this factor coming out CG mod d naught non-zero. So if this is non-zero, then first thing, this has to be non-zero. So in some sense, d naught is the first non-zero Fourier coefficient of G. And G is half integral weight form of weight k plus half. So I want to go to the integral weight. So I will do the 4 power G power half. So that was, so this will land in the 4k plus 2. So sorry, I think here something. So G is, so this is 2k and G is k plus half. So G power 4 will be 4 times k plus 2. So that is 4k plus 2. Yes, it is correct. Of label 4. And now G power 4 use a classical bound on the first non-zero Fourier coefficient of an arbitrary plus form to get that, since G power 4 also have the first Fourier coefficient non-zero as G, that 4 times mod d naught is less than or equal to 2k plus 2. So basically from here, from step 1, we conclude that the I can choose a fundamental discriminant d naught less than k, such that L half f tensor chi d naught is non-zero. Once that has been chosen, then next what I do, and now look at the set of set f2kn, the whole set of the AK eigenforms of label 1. And by using again Shimura-Conan isomorphism, we know that Gj, I use the Shimura-Conan isomorphism, I go to the half integral weight side, and we know that this Gj's, they will correspond to Fj under this isomorphism. and they will be the corresponding basis of Hecke eigenforms in the half integral bit side. So corresponding to this basis Fj, I got Gj in half integral bit, and now again Luo used Walsh-Purgey formula, relate the first movement of the twisted central L values this side to the coefficients of the half integral bit form. So basically we are transforming the problem this side to the problem of investigating the Fourier coefficients of half integral bit cusp forms. And now I want to get a good asymptotic formula for this first movement of central L values. So I will investigate this side and get for that. And this side, it's easier to handle since this side I know Peterson formula to handle this sum. Since coefficients, in terms of coefficients, I have the Peterson formula, which said that on the Sk plus half plus 4, the sum over the coefficients can be written in terms of the certain Klusterman sum and Bessel functions, and we know how to handle them. We have given ready-made bounds. If we use them, then we can get an asymptotic formula for this. And exactly that's what Luo does, and he used the known estimates for them to get that the left-hand side is equal to 4 times k minus half plus big O of k power 2 by 3. And once this is there for this side, then we know that this sum is related to the first movement of the central L values. So by using that relation, we get the first movement of the central L value twisted by chi d naught, which is equal to this much 4 times k minus half plus big O of k power 2 by 3. So, and now I will use for this denominator the norm of Fj, the relation with the symmetric square L function special value at 1, and bound for this, the symmetric square L function. That will be done in next step. So just here I use the relation of the norm of Fj with this symmetric square L function to write down the same first movement in this form. And next I use the bound, we use the bound for the L1 same square Fj, which is bounded from both sides k power minus in terms of the bit k. I will use this, and we use the Holder's inequality in this first movement to get something like this. So k is less than this side. This I take this as the first term, and second term will be the how many j's are there such that L half Fj tensor chi d naught is non-zero. So that's what it is written here. This is less than. K power epsilon is coming due to the denominator L1 same square Fj, and this is the cubic movement of the central L values twisted by chi d naught power 1 by 3, and how many g are there in F2kn such that they are non-zero, which are really taking part. Now here we are at the verge of getting the lower side estimate for this set. Only thing now we have to appropriately use something for this, and exactly for that Luo uses the estimate given by Yang, which is in 2017 recent result, and that said that the cubic movement is less than k times d naught power 1 plus epsilon. Please note that d naught is here the same d naught which I fixed such that the given F L half F tensor chi d naught is non-zero, and that is growing like k. So if I take that also into account, then and put this bound here, then we will get that number of G, sorry, here it is typo since I was in the mood of F2KP, maybe. So this is F2K1. So number of G in F2K1 such that L half G tensor chi D naught is also non-zero is greater than K power half minus epsilon. And hence Luo concludes that since with the D naught he started, it was already non-zero, this RKF, the number of G such that L half G tensor chi D naught is also non-zero is greater than K power half minus epsilon. So basically now what I want to emphasize here, I divided the proof into the 4 steps, and what I did, so what Luo did in step 1, first he chose D naught less than K such that L half F tensor chi D naught is non-zero. In step 2, he transferred the problem from central L values to the coefficients of the half integral bit cusp forms, and he got the first movement for the over the coefficients by using the Peterson formula in the half integral bit setting. And then in step 3 he comes back, sorry, in step 3 he uses the Peterson formula in the half integral bit setting, and in step 4 he comes back to the integral bit setting and he deduced the result. So step 1, getting the D naught less than K so that L half F tensor chi D naught is non-zero. Step 2 is kind of going from integral bit to half integral bit. In step 3, use half integral bit theory. In step 4, come back to the central L values and deduce the result. Now, if I want to repeat the same thing in the label aspect, then there are certain hurdles. And what are the hurdles? First of all, the Luo was dealing with label 1 and the other side label 4. And it's very nice Walsh-Furge formula and very nice isomorphism which goes from 1 to 4. So this side S2K1 and the other side SK plus half plus 4, perfect isomorphism, perfect Walsh-Furge formula due to Conan and Jagier, and no old form contribution. When we go to the label, then both side S2KN side we have to concentrate on the in S2KN side we have to concentrate on the new form subspace, and in the half integral bit side similarly we have to concentrate the corresponding subspace of the plus space SK plus half plus 4n. And then we have to get, and also we need Walsh-Furge formula to relate the Fourier coefficients of half integral bit side to this one. And there is a Walsh-Furge formula due to Conan at the label, at the higher level. But the point is there is a technical condition on the form which related to the free K involution, what eigenvalues should be. So, and another thing is that old forms contribution will also popped up. So to avoid that and to handle the label aspect, what Balesh did, he avoid these difficulties. He went to the theory of Jacobi forms in place of half integral bit modular forms. So first he doing the same thing. First he will start with 1F. Now this time new form of label P, and he will first use Walsh-Furge formula and the Walsh-Furge formula to get the least D naught such that L half F tensor chi D naught is non-zero. And while using Walsh-Furge formula, this time not half integral bit 1, he will use the Jacobi form Walsh-Furge formula. So there is if someone doesn't know Jacobi form, it's basically another kind of modular form which lives on the H cross C, upper half plane cross C, and transforms nicely with respect to the group matrices, SL2G matrices, as well as the Z cross Z lattices over C. So I'm not going to use anyway the theory of Jacobi forms here. Basically, just I want to emphasize here that the corresponding Walsh-Purge formula also hold good in the theory of Jacobi forms. And in the theory of Jacobi forms, the coefficients get related to the again central L values of integral bit cusp forms. As well as the advantage which he gets is that in the theory of Jacobi forms, Jacobi new forms theory is also studied. So in that study, it turns out that in these cases, in the cases of these bait and prime label, the Jacobi, the whole space of Jacobi cusp forms coincides with the space of Jacobi new forms. So here, when we start with, though we start with the label P forms, new forms, this side, other side, we have all Jacobi new forms. So we know we have the Peterson formula to use this side in the Jacobi form side, since otherwise the contribution from old form will also start coming in the Peterson formula. So basically, this condition, the eigen function with respect to WP with the eigenvalue -1 power k, it comes due to the nature of the Jacobi forms. Since basically the perfect isomorphism in the Jacobi form setting, it is not the full space S2kp to the Jacobi forms. It is from the space of Jacobi forms to a subspace of integral bit cusp forms, which really are eigen functions with respect to this with respect to free convolution with this eigenvalue. So that's why we are able to handle here only that subspace of the space of cusp forms. And this condition 2k should be restricted, this condition, due to the fact that the other side, in the Jacobi form side, exactly in these bait cases and label P, the whole Jacobi space, the whole Jacobi forms space coincides with the new forms. So he Balesh does appropriate changes by, and what he does basically in first of all, for the step 1, he also starts with NEF label P new form and relate the central L value at half to the Fourier coefficients of Jacobi cusp new forms, this time using the Walsh-Purge type formula for the in the Jacobi form setting due to Grass-Conan and Jagier. Exactly, use of the above formula is responsible for this condition, free convolution eigenvalue condition. And next, the in step 1, so in that's how he gets the least d naught less than p. This time he gets less than label power, I think 1 plus epsilon for any epsilon, such that L half f tensor chi d naught is non-zero. After getting that, he go to step 2, and in step 2, what we were doing, we were trying to go from relate the first movement of the L functions, twisted L functions at the central value half to the coefficients of the half integral bit modular form, here to the coefficients of Jacobi cusp forms. And this side, the coefficients of Jacobi cusp form to whose these coefficients are all coming from the Jacobi new forms. And for those Jacobi new forms, we have the Peterson Peterson formula involving the coefficients of those Jacobi new forms. So we use that to get the first movement of the central L values in the label aspect. Once that is done, then step is same. Only thing is that appropriately we have to modify and use the bound what we were using here. For example, the cubic movement bound in not in the bait aspect, in the label aspect and discriminant aspect, as well as in place of this symmetric square L function, it get replaced by the adjoint L function. So all those things are already in the literature. Especially this cubic movement was very useful, and it in the label and the discriminant aspect together, it is due to Petru and Young in 2019. And the estimate for adjoint square L values, it will help Balesh to deduce the label aspect result. Once so in the label aspect, he only difference is that he just replaces half integral Bates setting by Jacobi form setting. But Jacobi form setting also put certain conditions, especially on the Bates and the form to start with itself. To avoid all these, we don't go to half integral Bates setting or to Jacobi form setting. What we do, we try to work in the integral Bates setting itself. And we managed to do so by using the kernel function introduced by Conan. So at the end, let me just explain our idea of the proof, and I will just highlight the main part. And main part is that we don't go to half integral Bates setting or Jacobi form setting. We work in the integral Bates setting itself. Especially to avoid the contribution from the old parts, we use Peterson formula somehow and that we get by using the kernel function and contribution, and in that we are able to manage the contribution from the old part, and we get the first movement result with a nice asymptotic formula. So let me just highlight what we are going to do in our idea of the proof to overcome the restrictions on the form F and Bates K in the Balesh work. We work in the integral Bates setting, and our path of the proof is different from the approach earlier taken, except the last step. Once we get the first movement result, after that the step is same, using the cubic movement and using certain bound for the adjoint L function, and get the cardinality from lower side. So the first ingredient from beginning itself is a variant of the Peterson formula for integral Bates form. So in integral Bates forms also involving the Fourier coefficients, there is Peterson formula, but we avoid that since this involves contributions from the old form side also. And so what we do, we use the kernel function introduced by Conan. Kernel function is a so this is a function of two variables, we can understand, a complex variable S and an upper half plane variable Z. If you fix the complex variable in appropriate range, then it is in Z variable, it is a cusp form, and if I take inner product of this cusp form with any other cusp form, then this will give me the L function associated to that. So this is normal kernel functions, normal kernel, general simple kernel function. There is version of there is version of kernel function also, another version of kernel function, another function which gives me not just simple L value, which gives me twisted L value. So I have kernel, so we have kernel function that is again introduced by Conan, which if I take inner product of any cusp form with this kernel function introduced by Conan, it gives me the central L value of the L function attached to the central L value of the twisted L function attached to the cusp form F. So what we do, we take that kernel function introduced by Conan, whose inner product with any cusp form will give me the twisted central L value, write down that in terms of the orthogonal basis of the full space S2K P, And when we write down, obviously S2KP has two parts. One is old part and other is new form part. Now first our need is to get a suitable orthogonal basis of S2KP such that new form is separately, and the old form also, the basis which we construct for old forms, that also should be nice enough so that the inner product of the kernel function with those old forms also can be estimated nicely. So first of all, we find out a suitable orthogonal basis of the full space S2KP. Obviously, new forms are already there. F2KP is already there. What about old form space? Old form subspace. So old form subspace of S2KP. First, we decompose it in orthogonal decomposition. Like the first contribution is coming from S2K1, label 1 forms, and the other one is S2Kn under certain operator psi p, which is given here, even if it's not very important, this psi p operator. The thing is important here is that we have this orthogonal decomposition, and we will choose a basis of S2Kn, S2K1, Hecke eigenforms of label 1, and this basis will come from the Hecke eigenforms of in S2K1 / psi p. And here exactly the usual Atkin-Lehner decomposition, one need to have this into account, that S2K old P also, they are also decomposed into S2Kn with the direct sum of S2K1 / BP, but they conjecturally they are not expected to be orthogonal. So we want this kind of orthogonal decomposition where we can choose an appropriate orthogonal basis. And exactly this step is responsible for us not able to deal beyond P, since when we go to any other P, any other label N, then there are several, here only contribution coming in the old part, only contribution is coming from the label 1. But when we go to the arbitrary label, there are contributions coming from all the other divisors. So 1, and then other divisors in between. So we were not able to handle the contribution from those parts in the first movement. Now, once I have chosen this orthogonal basis, suitable orthogonal basis for old forms, and I have already orthogonal basis for the new form part, F2KP, then I take my kernel function, write down in terms of these bases. And what will happen? What coefficients will come out? Coefficients will be inner product of this kernel function with these basis element. And since kernel function has the property that will give us the central L values. So basically, it's handling the sum of the central L values at the lower label, and that we can manage at the label 1. Once we do that, then the other one already from beginning, we have got that to start with F, which we have started. For that, there is D naught less than P, such that L half F tensor chi D naught is non-zero. So once with that D naught we have started, please note that the kernel function will depend on D naught, which D naught you are taking. And once by using that kernel function, we have got the Peterson formula. I'm saying Peterson formula in that sense that writing kernel function in terms of the suitable orthogonal basis and taking and then looking at the coefficients. So that in that sense, I am saying, I have not put that thing here, otherwise it will look very lengthy. And I will estimate, obviously, this side I will have kernel function, other side I will have kernel, suitable orthogonal basis, and coefficients will be L values of those central L values of those basis elements. And now I will estimate. So I will compare first coefficient both sides. So the first coefficient of the kernel function that has in fact two parts. The first part of the first coefficient of the kernel function will give me the main term in the asymptotic formula, and the second part of the first coefficient of the kernel function and the contribution coming from the old part in the RHS, that will give me the error term, and in that way we write the asymptotic formula having into account that D naught is growing with the label P. Since if D naught doesn't grow with the label P, if I take the fixed D naught, then already first movement results are there in the literature, and they have been investigated in connection when we fix a character chi and we look at the number of forms in F2KP such that the central L value is non-zero, so single non-vanishing. In that connection, already first movement result is there. Only thing is that the conductor of chi is fixed there. It doesn't grow with the label. But we have to grow with the label since we are dealing with the simultaneous non-vanishing, and we can choose D naught only. We are allowed to choose D naught till P. We know that only till P, if we go, we can ensure that there is a D naught, that L half F tensor chi D naught is non-zero to start with. So that's why we differ from the existing one. And already I have told we use the particular variant of Peterson formula by using the kernel function, writing in terms of the suitably chosen orthogonal basis. And when we get the first asymptotic formula as a side product, we get this result that so that result is there. RPF is greater than P power half minus epsilon. As a side product, just be observed that if we take k greater than or equal to any integer and any fundamental discriminant D naught such that co-prime to the label P, and D naught is allowed to vary anything till P, then if we ask this question single non-vanishing, number of new forms of label P by 2k such that the central L value is non-zero twisted by chi D naught, it is greater than P power half minus epsilon. And I was searching that if this kind of result is already there when D naught vary with the label, and in label aspect how many single non-vanishing. So I couldn't get, I am not aware of any such result. What I could get while browsing is that if D naught is 1, this means asking L half F is non-zero, number of forms of label P. So in weight aspect, positive proportion has been established by Luo, and there is a paper by Ivanich and Sarnak in Israel Journal, I think, and their label and weight aspect both, and positive proportion. In fact, it is claimed that 50%, and I think I have to decode everything so to see the proof, but it's there, positive proportion for D naught equal to 1. And when D naught doesn't vary with P with label, it's just fixed in the beginning, the conductor of chi naught, then single non-vanishing result is there in label aspect greater than P by log square P. So it's something P power 1 minus epsilon, much better to say P by log square P, due to Duke for weight 2 and due to Akbari for any weight. So this was just side result, but the main result to count the simultaneous non-vanishing. With that, I will stop my lecture here, and thanks to everybody for your patience.
So thank you, Professor Shankhadhar, for a nice talk. So any question?
Thank you. It was a great talk.
Thank you, sir.
And I don't see anything other than technical complication to extending this to level PQ distinct dot primes. Is there anything more? You seem to have all the ingredients.
Nothing more. It's basically about handling the old farm contribution.
So there is a problem if you have PQ?
Yes, when I have PQ in the first movement result in the error term, basically I need label power some negative power. And there somehow when I go to the Q label new forms, then P get away. So I am getting Q negative power in the error term, but I need PQ negative power in the error term. So exactly that term coming from the old forms, but they are new forms of label Q, they are creating problems.
No, but PQ it's splitting into one P and Q.
Yes, but one form, then label P new form, then label Q new form.
You can't handle P and Q separately by this method?
No, we are not able to handle, sir. Exactly, that is the only hurdle.
Oh, I see. Also, yeah. There is some interference between this P and Q thing.
Yes. Once, sometime P get cancelled and sometime Q get away. So it is not in the form of label.
I see.
Something like I have to assume that the least prime dividing goes to infinity, which is not correct at all. So to do that.
Okay. Yeah. Thank you.
Thank you.
Yeah.
Hello, Karam.
Yes.
This is Sandeep.
I
had one question regarding Luo's first result. So you gave an asymptotic formula for central values of L function in terms of K, right?
This is Luo's result.
So after that, when you introduce the L half of G chi D naught, how do you retain the lower bound of K? How do you? So after that, you are putting holders, right?
Yes.
So when you add the extra G, I mean L half G chi D naught, then the lower bound K is still happening, or?
Yeah, K is still happening due to this main term.
Yeah, but what if, so now you are putting an extra term L half G tensor chi D naught, right?
Where? Here?
So how do you get this holders inequality below that lower bound of K? How do you get?
So this G is nothing but it's all FJs in this such that this central L value is non-zero.
Yeah, non-zero, no? The sign, how do you know they are the same sign? Means there can be different signs, no? When you introduce new term?
No, they are greater than or equal to 0 always, since due to the Walsh-Purge formula.
Okay.
Yeah.
For the twist, this is non-positive, I mean non-zero.
Yeah. So only thing I want to count which are non-zero, but they are already non-negative.
Okay, fine.
Yeah.
Any other question?
Hello.
Yes.
Thanks. Very nice talk. So this is maybe a naive question, but when you're looking at the product, you're seeing that both are non-vanishing. That is the thing you're considering right now. Is it of any interest to see when exactly one vanishes, and like are these kind of methods going to be useful? I mean, is there any modification?
So here exactly this set.
Yeah, like suppose we want to say F and G inside this set such that exactly one of them, vanishes, something like this.
So exactly one of them vanishes already studied. So your question is that in what sense it is useful, having simultaneous non-vanishing?
No, I'm saying that suppose you change the question, is it interesting at all? And then whether the method can be used in that way.
Okay. So can you repeat your question? How to change the question?
So you take set of all F and G inside such that in the you're talking of exactly one of these two L functions vanishing. Other one does not vanish. Like if F wala twist vanishes, then the G one does not, and the other way around, something like that.
Yeah. Yes. So you want to count how many F, G, etc. are there. So let's start with 2. So how many pairs are there which are central L value non-vanishing for the same D? Yes, that is interesting. But here the point is this method won't handle that when you vary F and G both, since according to F, D will vary, and then according to G, I have to fix. So here in this method, I am fixing F and fixing D according to that F. And then I am doing analysis for all G. So obviously, so the point is that in half integral bit, it's a big question that whether there exists one single fundamental discriminant D naught such that all basis coefficients are non-zero at that D naught, and they turn out to be related to the central L value. So if we can find one single D naught such that for all F, G, H, it is happening all the basis, then certainly it's very interesting towards half integral bit side as well, that you get normalization that side.
Okay, but counting the F and G, the pairs would be kind of
yes. Means this method won't handle that.
Okay. Okay.
Yeah. Thank you.
So any?
Can I ask? Yeah. So Karam, one more question.
Yes.
So what is so regarding Lewis result and your result, P power half minus epsilon or P power half minus epsilon is the expected thing, or is it bound to be improved?
No, it's certainly expected much more. It's expected positive proportion, I think.
So in the level aspect, what is the positive proportion would mean?
So greater than constant time P.
P. Okay.
Yeah. It is much worse.
Instead of using this Peterson formula, if we use approximate functional equation or something, can we modify it?
I don't know if we can modify something and get better. Certainly, it will be good to see, but I don't know.
Okay, thank you.
Yeah.
So, any other question?
So, hello.
Yeah.
So, does this method gives you the lower bound in terms of both weight and level?
No. So when we do our calculation, we have to treat K as constant at several places. So we have to fix K.
So any other question? Oh, no. So if there is no further question, so let us thank the speaker once again.